This is Georgia Tech Physics 2 Lab 3 Circuits by Ryan Perella. The purpose of this lab is to predict the circuit behavior containing resistors in series and parallel resistors, use multimeters to measure the value of conventional current and potential difference in the circuit, and examine the behavior of resistors and capacitors. Our system is a circuit and our surroundings is everything else. Review of the results. Charge and discharge times for the capacitor were similar, not exact but close enough. Some of the potential difference was 0. Resistors were 48 ohms and 102 ohms. Wire had 0 ohms, and then charging and discharging capacitors approximately equal to 10 seconds, and our current is 0.02 amps. Fundamental principles were node rule. The current flowing into a node must be equal to the current flowing out of the node and results in a conservation of charge. Loop rule. The sum of all electric potential differences around a loop is equal to 0. Assuming the start and end points are the same. And then Ohm's law, the current through a conductor between 2 points is directly proportional to the voltage across the points, or V equals IR. Here is a picture of our lab. You can see us using the circuit to light up the light bulb, and then it would dim as the charge negates. Here you can see an illustration of our circuit, and we're going to predict the currents of I1 and I2 that we measure in the 2 ammeters. So we have two 1.5 volt batteries. Our total is R1 and R2. We have 47 ohms and 100 ohms computationally. V equals IR, which means I equals V over R, which means 3 volts divided by 147 ohms gives us 0.02 ammeters. Now, due to node rule and conservation of charge, reversing the connections of 1 ammeter changes nothing in this experiment. What if we replace 1 ammeter with a voltmeter? What happens? 1, the ammeter reads 0 amps because the voltmeter has very high resistance, and 2, the voltmeter continues to read -3 volts because there's no voltage drop. Now, what is the voltage drop across each part of the circuit? Loop rule has VB minus IR 47, and then IR with 100 ohms equals 0. You can see the math here. VB is the area from A to B, and it's 3 volts. And when we do the math, we get the current is 0.02 amps. Now, when you attach a voltmeter, the circuit changes. So the ammeter reading doesn't change because a voltmeter has a very high resistance. So we're still going to read the 3 volts, which is we get from 1.5 volts. So little charge actually flows through it. So that's why we see the change in charge. Now, what happens if we replace the voltmeter with ammeters in parallel with a 100 ohm resistor? What happens to the current flowing through the ammeter? So the ammeter has low resistance, so the electrons will flow through the ammeter instead. This will in turn lower the overall resistance of the circuit, and that leads to 2. The total resistance of the circuit is now only 147 ohms instead of the previous 147 ohms, so it directs a different way. What is the total resistance of each circuit element? Our resistor with 47 ohms is 48 ohms in this example. The 101 in actuality we measured to be 102 ohms. The resistance of the wire is 0, and the resistance of the ammeter is also 0. Now, resistance capacitors or RC circuits. So a 9-volt battery, a 200 mF capacitor, and 30 ohm light bulb are connected to a series. What is the RC value? We expected it to be about 10 seconds, and then experimental, we do 1 over the slope, and we got 11.4 seconds. Now, this is old equipment, so the numbers were a little off, but it was close to that 10-second prediction. Now, some potential errors. 1 is human error. Obviously, in stopping the stopwatch and capacitors from discharge time, that could lead to why that was 11.4 seconds and not 4 seconds. We started the stopwatch slightly off and ended it slightly off because we were eyeballing the light bulb with it. So that could be a little off, human error. And then 2, the model is not 100% accurate of real-world scenarios. There are other forces that we are simplifying to make our lives easier. Discussion question: what if you charge a capacitor with no resistor in the circuit? If you charge a capacitor without resistor, our ideal model says that it'll reach full charge instantly. That's because the time constant RC dictates charging speed, and if R is 0, the constant is 0. But that won't happen in real life because you can't have a circuit with 0 resistance. You're always going to have just a little bit. Components like the wires, batteries, and ammeters all have a small built-in resistance. Even if it's almost negligible, it is still there. While this collective resistance is tiny, it's enough to ensure the charge up isn't truly instantaneous. Though the time is so quick, we usually consider it negligible and effectively zero. Thank you for watching.